All right, today we're going to demystify one of the most powerful tools in all of machine learning, classification. At its core, it's really just about teaching computers to do something we all do instinctively every single day, sort things into different groups. But when computers do it, they can uncover these incredible patterns and make predictions that can save time, money, and yeah, even save lives. So how does it all work? Well, let's dive in with a situation where getting it right is literally a matter of life and death.
So to really get a handle on the power of classification, let's look at a scenario where a single prediction isn't just important, it's absolutely critical.
Okay, put yourself in this situation. You're running a busy hospital. You've got a limited number of ICU beds, but dozens and dozens of patients in the general wards. The challenge is just immense, right? How do you know which of those patients might suddenly take a turn for the worse? Predicting this accurately could be the difference between proactive care and a full-blown emergency. This is exactly the kind of high-stakes sorting problem that machine learning was built to solve.
So how do you even begin to tackle a problem like that? Well, you can't just hand a computer a list of symptoms and hope for the best. You actually have to teach it how to recognize the hidden patterns that signal a high risk. And this whole teaching process has a name. It's called supervised learning.
The best way to wrap your head around this is with a simple teacher-student analogy. The machine is our student. We, the humans, we're the teacher, and we feed it thousands of past patient records. Now here's the crucial part. For each of those records, we provide the correct answer, a label that tells the machine whether that patient ended up needing ICU care or not. By studying all these labeled examples, the machine starts to figure out the rules all on its own.
Okay, so supervised learning basically splits into two main camps. Over on the left, you've got classification. The whole goal there is to predict a category, a label. You're asking questions like, is this tumor malignant or benign? Is this patient high risk or low risk? Then, on the right, you've got regression, which is all about predicting a specific, continuous number, like what's the exact price this house is going to sell for. So for our hospital problem, right, we need to predict a category, needs ICU or doesn't need ICU, which means we are firmly in the world of classification.
So, what does this actually look like in practice? It's a pretty straightforward four-step flow. It all starts with that labeled data, all those historical patient records where we know what happened. Then we pick an algorithm, which is basically the strategy the machine will use to hunt for patterns. That algorithm then crunches all that data to create a model, which is really just the set of rules it's learned. And finally, the payoff. We give the model brand new unlabeled data, like a new patient who just walked in, and it spits out a prediction. All right, so what do these algorithms actually look like? Let's start with one of the most intuitive and honestly simplest methods out there, k-nearest neighbors, or as we call it, KNN. The whole idea behind KNN is perfectly summed up by that old saying, birds of a feather flock together. It works on this really simple assumption that you can figure out something new and unknown just by looking at the known things that are closest to it. It's kind of like judging a new restaurant based on the opinions of your three closest friends.
Okay, let's make this real. Imagine this chart shows a bunch of students who we've already classified based on their scores. Now along comes a new student, Josh. Based on his scores, he lands smack dab in the middle of our chart. Looking at him in isolation, we have no clue where he fits. But with KNN, we don't have to guess. It's a super simple three-step process. First, we just pick a number, K. Let's go with 3, which means we'll look at his 3 closest neighbors. Second, the algorithm calculates the distance from Josh to every other student and finds the 3 that are nearest. And third, those 3 neighbors get to hold a vote. In this case, 2 of his closest neighbors are intels and 1 is a leader. With a 2-to-1 majority, well, the intels have it. KNN predicts that Josh is an intel. Simple, right?
What's really interesting about KNN is that it's called a lazy learner. And here's why. It's not like an eager learner that does all its homework up front to build a nice, neat model. Nope. KNN basically procrastinates. It doesn't build a model at all. It just stores all the training data. Then, and only when you ask it to make a new prediction, does it finally do the work of calculating all those distances. This is great, because it means there's no training time, but it can also mean that making predictions is a bit slow if you have a massive data set.
All right, let's totally switch gears now and look at a completely different method, one that feels a whole lot more like our own internal logic, the decision tree. I mean, think about it. When you're faced with a big, complicated decision, what do you actually do? right? You break it down, you ask a series of simple, sequential yes or no questions. If the answer is yes, you go down one path. If it's no, you go down another. And that is precisely how a decision tree works. It builds a model that looks just like a flowchart.
This table is the perfect example. Let's try and predict if a candidate named Chandra will get a job offer. We're just going to follow the path down the flowchart. So, starting at the top, is her aptitude high? Her profile says yes. Okay, we continue. Next question, is her communication bad? Yep, so we keep going. And the final question, is her CGPA high? Yes, it is. And that path leads us straight to our final prediction, job offered. It's just an incredibly intuitive way to map out complex rules.
Okay, so KNN and decision trees are kind of the building blocks, but the field definitely doesn't stop there. People often use even more powerful tools that build on these core ideas. So let's take a super quick look at two of the heavy hitters. First up, you've got the random forest. The logic here is pretty simple. If one decision tree is good, why not use hundreds of them? A random forest algorithm does exactly that. It builds an entire forest of slightly different decision trees, and then it pulls all of them for a final answer. It's basically the wisdom of the crowd approach, and it makes its predictions way more robust and accurate.
And then there's the support vector machine, or SVM. Now this one's a little more geometric. Imagine all your data points plotted out on a graph. The SVM's goal is to find the single best line that separates the two different groups. So what does best even mean here? It means finding the line that creates the widest possible street, or margin, between the two classes. This huge buffer zone makes it incredibly powerful for finding clear boundaries even in really messy, complex data.
Okay, so we've been talking a lot about the theory, right? But the true power of classification, where it really comes alive, is when you see how it's actually transforming the world all around us. And the thing is, classification is already everywhere. You're using it every single day, probably without even realizing it. It's that silent algorithm that flags a potentially fraudulent charge on your credit card. It's the engine that personalizes your social media feed to show you exactly what it thinks you'll find interesting. But it also has these incredible life-saving applications, like helping doctors spot cancer cells in medical images, or even just making sure your mail gets sorted correctly. Every single one of these is a sorting problem, and it's being solved at a scale and speed that's just mind-boggling.
And that really brings us to a final thought here. From our hospitals to our social media, classification is this amazing tool that turns raw data into real decisions. And as these algorithms get even smarter, even better at categorizing and sorting our world, it really makes you wonder, what's the next big problem they're going to solve? What's that one prediction you really wish a machine could accurately make for you? Thanks for following along.